In chapter 19, you're trying to put branches onto benzene rings. The problem is that benzene is aromatic, and so it's very stable, and it's not very reactive. You might remember from Organic Chemistry 1 that 95% of reactions happen because opposite charges attract. Negative charges are attracted to positive charges. Things that have slight negative charges, or a lot of electrons in them, are called nucleophiles. You'd recognize those because a nucleophile will either have a full negative charge, a partial negative charge, a lone pair, or a pi bond. Those are the different ways you can recognize those negative charges. Anything that has a positive charge is an electrophile, and you'd recognize electrophiles because they'll either have a full positive charge or a partial positive charge. And 95% of reactions happen because nucleophiles attack electrophiles. And you show the attack with those curved arrows, the movement of electrons. So, using that framework from Organic Chemistry 1, if you think about benzene, we've talked in a previous chapter about benzene's aromaticity and special stability. So it's not very reactive. It's not very reactive, but if you were to classify it as either a nucleophile or an electrophile, you could go through each of these terms. There's no full negative charge on benzene. There's no partial negative charge on benzene. There are no lone pairs on benzene, but there are pi bonds. So each of those pi bonds in benzene would count as a potential nucleophile. So benzene as a whole is a nucleophile. If you go through the same process to see if it has any electrophilic centers, there's no positive charge, there's no full or partial positive charge. So benzene is really a nucleophile because of those pi bonds, those places where you have extra electrons that could be attracted to positive charge. Okay, but we also said benzene is aromatic and so not reactive, and so another thing we can say is that benzene is a poor nucleophile. It is a nucleophile because it has the pi bonds, but the pi electrons in those bonds are really stable, so they're not going to want to react with anything, and so this is not going to be very reactive. It will be a poor nucleophile. And so normally that just wouldn't react. In order to make benzene react with something, because we're trying to put a branch on benzene, in order to make benzene react with something, we have to really entice it. We have to give it some sort of amazing electrophile with a full positive charge, or something really close to it. Because if you have an awesome electrophile, if the electrophile is really reactive, then it'll react even with a bad nucleophile, like benzene. If it's really positive, really attractive, even benzene will attack it. And so the first step in this mechanism is the creation of a really good electrophile. That's sort of what's happening in this top step up here. Let's draw that out, think about what's happening there. In order to, here I'll just add a page here. So in order to, in other words, in order to react something with benzene, we need to create this awesome electrophile. Now, bromine all by itself, molecular bromine, two bromines bonded together, is not the best nucleophile. First of all, the bond, each of the bromines has the same electronegativity, and so this bond is perfectly nonpolar. There is no partial charge on the opposite sides of those bonds. But one thing you might remember from your Organic Chemistry 1 class is that the halogens in general, and therefore bromine in particular, are really big. That's why they were always such good leaving groups. So I'm going to focus on this bromine, and I'm just going to draw that bromine as an atom, as a really, really big atom. And big atoms have a special property. The property is called polarizable. Big atoms are polarizable. What that means is, when they come close to some sort of charge in the outside world, it's possible for all the electrons that were spread out, it's possible for them all to rush toward the side of the atom that has the charge, the positive charge. And because the atom's so big, they can all get close to the charge without getting too close to each other because they repel each other. It's sort of like you have a spectacle here, and it's happening on a really big stage, so a lot of people can get really close to the stage. Compare that with, like, if you had a small atom. If you had a small atom, it's like having a really small stage. In order for people to get close, they'd have to get really crowded together. But then they'd push each other apart, and so not as many people would get close to the stage in that scenario. In the atomic scenario, not as many electrons would get close to the positive charge. So when all the electrons rush to that side of the atom has a slight negative charge, and the opposite side of the atom has a slight positive charge because it's missing its electrons. So we're used to seeing dipoles in bonds. You have two different atoms of different electronegativity, and the difference in electronegativity creates a dipole over the whole bond. One atom on one side of the bond is slightly negative, the other atom in the other side of the bond is slightly positive. But here we're seeing a dipole on one atom, and another way of saying that is that atom that's capable of forming dipoles is polarizable. Now, that does give the bromine a slight charge, but that charge is not going to be strong enough. This all by itself is not big enough. That positive charge is not going to be big enough to attract a really bad nucleophile like benzene. So we have to turn this bromine molecule into a better nucleophile, or a better electrophile, so that even benzene, which is a poor nucleophile, will react with it. And to do that, you just need some sort of a metal. And we'll have it bonded to 3 bromines. So you might see it sometimes as FeBr3. You might also see it as aluminum Br3. It doesn't matter. You just need a metal that's going to form these 3 bonds. Either one of these would work. Let's do it with the iron. So anytime you see a metal in organic chemistry, you should be thinking, this has really low electronegativity. It's going to give its electrons away, and it will become slightly positive. The bromines are pretty electronegative, so they're going to gain those electrons, become slightly negative. And so you have that positive charge on the iron. Now this iron is bonded to 3 atoms and has no lone pairs, so this molecule is trigonal planar. This is flat, like a pancake. And so the bromine molecule can come close to it, and one of the bromines can get close to the iron. Now, the iron has a slight positive charge. So what happens in that big bromine? The same thing we said happens a second ago. The bromine is really big, so it's polarizable. The electrons in the atom feel the positive charge on the iron, and they all rush to the side of the atom that's facing the iron. And so bromine develops a slight negative charge toward the iron and a slight positive charge on the opposite, away from the iron. Now that's just that one bromine atom, not the bromine molecule. And so you have this induced dipole on the atom. And now that you have the slightly negative charge, with all those electrons, that can act as a nucleophile, and the bromine ends up attacking, those electrons end up attacking the slightly positive iron, the electrophile. So without visualizing the actual atom and the dipole, you would have that. So that's the first step. And the one result of this is that, so the result of this is that you'll have the 2 bromines, but now they're bonded to that iron, and the iron still has the 3 bromines that were bonded to it. The iron has extra electrons around it now than it did before, so it has a full negative charge, and the bromine has lost some of its electrons. Electrons it had all to itself are now being shared with the iron, and so it has a full positive charge. So this molecule is really unstable. You have a full positive charge on an electronegative atom. That atom wants electrons, and you're forcing it to lose them. That's how it's getting this positive charge. So that's really unstable. And you have a really unelectronegative atom with electrons around it that it's trying to hold on to itself, but it can't do it very well because it has such low electronegativity. So this very quickly crumbles. It can crumble in a few ways. It could crumble where these electrons go back onto the bromine, and then we end up with our original stuff. So in that case, the reaction doesn't go anywhere. And so both of these species will exist at equilibrium at any given moment. Some of the molecules will be stuck together, and some of them will be apart. But another way that the ones that are together can crumble is that the electrons on this other bromine can go toward the bromine with the positive charge to help to stabilize that positive charge. And so what you end up with is this bromine on the end now only has 6 valence electrons, so it has a full positive charge. The iron half of the molecule still has those 4 bromines. It's more stable than it was above, but it's still unstable because the iron still has that negative charge. The bromines are at least stable, but the iron has that negative charge. Well, we'll discuss what happens to that in a second. But right now, we formed this bromine with this full positive charge. That's what we wanted this whole time. We wanted an awesome electrophile with a full positive charge. We said electrophiles either have full or partial positive charge. The better electrophiles will have this full positive charge, and that's what we need. Because the nucleophile we're working with is not very reactive because of aromaticity. So this is this first step, and you'll notice this pattern for all of these mechanisms where you're adding things onto this benzene ring, or for most of these mechanisms where you're adding things onto the benzene ring. The first step is to form a really awesome electrophile. Okay, once you form the awesome electrophile, that can now react with benzene. So we'll bring benzene into the picture. And it's the electrons in the pi bonds of benzene that will attack our electrophile. These electrons make benzene nucleophilic, and so those electrons end up attacking that electrophile. Now, when you get that, all of the carbons on benzene have a hydrogen. Let me just draw this hydrogen here. We'll just keep track of it. It doesn't matter where you put the benzene on the ring, because where you put the bromine on the ring, because all of the positions are symmetrical. I'm just going to put it at the top, and if you put it at the top, the electrons that were being shared by 2 carbons just end up going onto one of them, so the other one is missing those electrons now, and it has a full positive charge. So you end up with this intermediate, unstable intermediate. Now that you would recognize has a resonance pattern that you learned in Organic Chemistry 1 in Chapter 2. One of the resonance patterns is if you have an allylic positive charge. The reason you have resonance when you have this is because, remember, that positive charge is an empty p orbital, and these p orbitals here, there are parallel p orbitals there to create the pi bond. So you really have 3 parallel p orbitals here that allow electrons to spread out. And what resonance does is it tries to describe that spreading out. Because right now, the way this is drawn, it seems like the electrons are localized. So to show that they're spreading out, anytime you have that allylic positive charge, that's a positive charge that's 1 atom away from an atom in a double bond. If you go 1 atom down, you're at an atom in a double bond. Whenever you have an allylic positive charge, to show the other resonance structure, to show that the electrons are spreading out, you move the electrons toward the positive charge. Now remember, none of these resonance structures ever exists. The true structure is the only structure that ever exists is going to be the average of each of these. And so that's what this special arrow is telling you. Notice it's different from an equilibrium arrow. The equilibrium arrow means reactants are turning into products and products are turning back into reactants. But this resonance arrow means the true structure is only the average. Take the average of everything inside of these brackets. So if those electrons move over, everything else in the molecule stays the same. Just the electrons move And the atom that now is missing electrons, and so has a positive charge, changes. So now we have another positive charge, and this positive charge is allylic to yet another pi bond. It's one atom away from an atom in a double bond. And so again, anytime you have that allylic positive charge, it's special because you have those p orbitals that are all parallel, and so the electrons can spread out over those atoms. So you draw the movement of those electrons with these resonance structures. And to draw the new resonance structure when those electrons move out, you take the electrons in the pi bond and move it toward the allylic positive charge. So that leaves you with this third resonance structure. Another thing to remember is just the meaning of resonance. Like, what does it mean that we're able to draw resonance here? When you draw resonance, you're drawing electrons spreading out, and whenever charge spreads out, that stabilizes a molecule. And so the more resonance structures you have, the more stable the molecule is. The fact that we're breaking aromaticity means that we're turning something that's really stable into something that's really unstable and therefore disfavored. It's the fact that you have these resonance structures that allows this reaction to go forward at all, because it helps to stabilize this intermediate, which means you lower the energy of it, and so it's easier to make the transformation happen. These resonance structures, the true structure is only the average of them all, but which is why the resonance structures together are referred to as one thing. They're referred to as a sigma complex. So the sigma complex is that resonance stabilized intermediate that you get right after benzene attacks its really good electrophile. Okay, so this is what we're going to notice, this pattern in all of the mechanisms in this whole chapter. You have this first part, sort of like a prelude, where you create an amazing, mouth-watering electrophile. You react it with benzene, and you always get this sigma complex. Then, to restore aromaticity, you add some type of a base. Remember, bases are things that accept H pluses. They take hydrogens without their electrons. And so what we're going to do is take this hydrogen that's on the carbon where our bromine added. That's now going to be under attack. And what we have available still is the metal complex that it was unstable anyway. If you zoom in on that, think about what's happening here. All these bonds have negative charge. They're all repelling each other. Ideally, all these electrons would fly off in opposite directions in the universe and never see each other again. But they're being held together by the nucleus of the iron, the protons in the iron atom. But iron is a metal. It has very low electronegativity. It does not attract these valence electrons very much. And if you think about the reason why, that's because iron is a pretty big atom. It has a lot of protons in it, but it has a lot of electrons around it too, and those wrap around around the nucleus. If this is the iron nucleus, it has a lot of electrons that wrap around in layers. So the outermost layer doesn't really feel the positive charge of the nucleus as much. So this iron has very low electronegativity, and these bonds all push on each other. Eventually they push each other apart so much, iron can't hold on anymore, and one of the bromines pops off. And so the bromine, with this bromine, it could have been any of them. I'm going to choose the bromine on the left. That bromine gets kicked off the molecule. The repulsion from the electrons in the other bonds is just too much. Iron isn't electronegative enough to attract it enough to keep it there. So it gets kicked off the molecule, and it uses its electrons to steal that hydrogen. So this whole thing is acting as a base. The electrons on the hydrogen go back to restore aromaticity, so that you're left with bromobenzene, you're left with you create that aromaticity of benzene again, and you have that original metal compound that you had to begin with. Notice this is the exact same molecule we started with at the very top. A molecule that if you use a molecule to make a reaction happen and you produce it again as a product, it's a catalyst. It's making the reaction happen, but it's not getting used up as it makes the reaction happen. And so it's really just a catalyst. It's a metal catalyst here. And so that's how you're able to put this bromine on a benzene ring. Now we could have done this same exact mechanism with chlorine. You could have a Cl2 and FeCl3, just replace all the Brs in the whole thing with chlorine, and you're good. And remember, you could do the same thing with just a different metal, like aluminum. So there are some variations, but the concept is the same. You create an amazing electrophile, you react that with benzene to get the sigma complex, resonance stabilized sigma complex, and a base steals one of the hydrogens from the sigma complex to restore the aromaticity. And so that's what hopefully that gives you some insight into what's happening in this mechanism here. You turn bromine into an awesome electrophile. The benzene attacks the electrophile. You get the resonance stabilized sigma complex, and that unstable metal compound acts as a base to restore aromaticity. So technically you also produce this HBr, that's this Br and H, but the truth is this is our really important molecule, and you should also know that the FeBr3 will be reproduced. This way you recognize that that's a catalyst. So there's only one way to draw the mechanism for the bromination of benzene, pure benzene, and it is exactly this. So that's the exact thing that you would need to be able to draw if you were asked on a test, draw the mechanism for the bromination of benzene.